Guys, again, as thoroughly and efficiently as we possibly can. Let's answer questions relative to entropy. And then, guys, today what we're going to do is we're going to talk about quantifying entropy. It'll be a very brief conversation because it's basically everything you've done with enthalpy, only we're looking up different numbers. It feels a lot like the Hess's law calculations we did. And then, guys, when we're done with that, we're going to get into Gibbs free energy, which again is our only real predictor of spontaneity, which we know is the big idea for chapter 19. We're going to talk about that with the bulk of our time, and then we'll call it a day then. And we will do Pride, and then Cody and I are headed to Brigham City to go duck hunting. Bye-bye. So, what do you got, guys? Questions? Robbie. 11D. 11D. Yeah, go ahead. Hi. Does this say Christian? He just left. Thanks. Go ahead.
So I was just like, because I never figured out something or lightning actually it's weird to think about, like the cause of what's going on. And so I was thinking too much about it. I didn't get that it was spontaneous.
What? Actually, it is. He says his name Christian. Yeah. Thanks for checking. Yeah. So what do you want to talk about?
I just don't understand how it's...
Okay, so the question says what?
Spontaneous or not spontaneous?
Okay, so do you have to do anything external to make lightning happen? See what we did right there? 1.21 gigawatts. Okay, so, but the idea seriously, Robbie, is, and again, it depends on what we're calling system and surroundings, right? But we know that lightning happens spontaneously. There are things, processes that are taking place that lead to it, specifically updraft, which creates friction, which creates static charge, on and on and on. But that lightning bolt jumps from a place of higher potential to lower potential, and it does it without any external influence. The things that create those potential differences certainly require outside intervention, but lightning itself is something that happens spontaneously. Okay, go ahead. Guys, does anybody else want to talk about anything in 11 while we're there? Okay, so 23. What about it?
I don't know what an isothermal process is, and I don't know
okay.
what that's saying, and also why it works, even if I didn't know it.
Okay, so here's the problem. I forgot to use the term isothermal when we looked at an isothermal process. We talked about what it means, but we didn't give it this name. So remember when we had the blue, are you with me? This is blue. We had the blue thing, and we had the not blue thing, and this contained a gas, and this didn't, and then that was an isothermal process. And simply what that means is there's no exchange of heat. So iso means that it's not taking place. So if you've done it means not moving. So if you've done isometric exercises, which were all the rage for a while, you push arms together and nothing's moving, but you're still exercising. They were called isometric exercises. The thing that iso means is no movement. So when we say isothermal, we mean no movement of heat. So we're talking about a process that happens, but heat is not being transferred. Does that provide enough background?
No.
Okay.
Because now I understand what it is. But
Okay.
it says, how do you calculate entropy for an isothermal process?
Mm-hmm.
And then it says, by knowing the amount of heat transferred in the process from reversible. Like, I just don't understand.
Yeah, and so this is and to be honest with you, this is something we don't have to do a super deep dive on, but the idea here is, and we're going to talk a little bit more about this later, and this is not going to do a deep dive. I should probably just get rid of 23. But frankly, the answer is, it's hard to measure disorder. But what we can do is we can actually track down energy as if it was being changed through the avenue of heat and understand that it's actually a reflection of disorder. And I know that that's a wildly unsatisfactory answer. I'm getting rid of 23. Let's just note to self. Yeah, it's frankly not I think it just creates more confusion than not. So let's do this. 19, 23, kill it. Yeah, we're just going to, will you just let me say that? We're just not going to, yeah. Okay. What else, y'all? Go ahead, sir. 19A? This guy? Oh, yeah, this was interesting. We were talking about this. Who was I talking about? Were we talking about this one? We were drawing pictures on paper with circles. It was you guys. Was that right? Okay, so on number 19, it says this. Was it 23? Chapter 19, number 19. So it says, consider a process in which an ideal gas changes from state 1 to state 2 in such a way that the temperature gets colder. And then the question says, describe how this change might be carried out while keeping the volume of the gas the same. So the idea, I'm not in a position where I can draw, so let me change that, and I'm just going to make a mess. So the idea is this. So 19A, so the idea is that we have got a gas, and we've got two gas. We've got state 1 and we've got state 2. In state 1, it's hot. In state 2, it's less hot. So the temperature is going down. But what we're saying is the volume doesn't change. So it's like a rigid balloon that doesn't shrink. And so the idea is that if we're going from something that's hot to something that's cold, if the volume can't change, then the pressure is going to go down. The molecules will come closer together. They'll push out with less force, and the pressure will go down. The other option is, and I think I mentioned this, it could also leak. But assuming that the number of molecules is the same, in this change, the pressure would have to go down. So, anything else, y'all? Are we good? Bailey, what about it? All of it? Oh, yeah. So let's talk about you've got your books open to page 818. Guys, we're actually going to look at N-pentane and neopentane again when we talk about intermolecular forces. So this is a conversation worth having. So it says this. This is a statement, and you need to know this. So here you go. Isomers are, and guys, this is a definition you need to know. Isomers are molecules that have the same chemical formula. In this case, C4H10. Okay, they have the same chemical formula, but C5H12. C5H12, but the molecules are organized differently. So for example, pentane can either be the left-hand structure, which is called N-pentane, or it can be the thing on the right, which is called neopentane. And then the questions go on and it says, do you expect a significant difference in the enthalpy of combustion of these two reactions? So guys, when we talk about enthalpy of combustion, and this is an important idea, enthalpy is heat, enthalpy changes. So guys, when something burns, why does it give off energy? Bonds forming, right? So when something combusts, carbon dioxide in water is formed, energy comes out as those bonds form. But that's only half the story, because while energy is released when bonds form, what about the reactants? They've got to take in energy, and that's endothermic. So guys, regardless of whether we burn N-pentane or neopentane, we're going to get the same products, and therefore the same amount of energy out. What about the energy that goes in? Will it take a different amount of energy to break these two things down? No. We are breaking carbon-carbon bonds, and we are breaking carbon-hydrogen bonds. The bonds are similar in strength, in polarity. We're breaking the same kinds of bonds. Therefore, the energy in is going to be the same, which kind of sounds like the conversation we had, right? About the weak and strong acid in the previous, same conversation, only there the bonds we're breaking are different. But guys, in this case, the bonds we're breaking are the same. The energy should be the same. Is that okay? Okay, now guys, read part B. It says, which isomer do you expect to have a higher entropy? And guys, they are not the same. So let me just lay this on you. Guys, the N-pentane, y'all looking at it? The N-pentane is stretched out. The neopentane is all balled together. And guys, this is the fundamental idea. When something is balled together, it has less freedom. It has fewer options in terms of the different ways it can be organized. Those bonds can sit there and wiggle, but because those bonds are all organized around that central carbon, it's relatively rigid. But guys, when you look at N-pentane, that thing's all strung out and it can twist and spin and do all this funky stuff. And as a result, the N-pentane has more possible, microstates, and as a result, it is more disordered, or it could be more disordered. So the entropy on the thing on the left is higher than the entropy of the thing on the right. So the bottom line, guys, is the more strung out something is, the higher its entropy will be. The more balled together, the lower its entropy will be. And what you're going to find in coming chapters is that actually means that the N-pentane has a higher boiling point because its electrons can be in more wacky places, then that makes it more polar. And we'll talk more about that later. But that was, Bailey, an important one to talk about. So guys, what else? We good on 6? We're going to give this 2 more minutes and then we're done. Go. Okay. So should we read the question or can we just talk about the principle? Are you sure? Okay. So guys, the principle is this. This is the second law of thermodynamics in a nutshell. Ready? It don't matter what the heck is going on, entropy is going up. That is the redneck version of the second law of thermo. It does not matter what, and this was that sort of weird thing that I was alluding to at the end of class that you guys didn't find interesting, but it was weird. I had a general chemistry student come and ask me the exact same question. It was weird. Anyway, so guys, the idea is this. The second law of thermo says it don't matter what's going on. The entropy of the universe is always going up. So now you ask yourself, well, wait a minute. Isn't life an exception to that? Isn't life the process of creating order out of chaos? And the answer is yes, it is. Guys, literally, that's what's happening inside living things is we take this jumble of atoms and organize them into cells and proteins and all the things that make us alive. So life is an organizing process. And there are other processes that are organizing processes. But guys, the idea is this. As those things are creating organization, somewhere in the universe, there's got to be an offsetting process that causes disorder to go up as much as that organizing process is decreasing disorder. And that's what letter C is all about. That anytime, guys, we've got a decrease in disorder, there has to be an offsetting increase in disorder somewhere else in the universe. Where is that for most things for us here on Earth? The sun. What's that? Oh, okay, so I don't like the way I said that, but maybe it's because of the wording of the question. But the idea, we're talking about a decrease in entropy. Entropy is disorder, right? So if we've got, let me see if I can draw it. See if, and then maybe you can help me say it better. So I'm going to do, okay, so say that we've got a process that's creating a decrease in disorder. Then somewhere in the universe, there's got to be an increase in disorder that is greater in magnitude than this decrease. So if the entropy change for the system is this, we know the decrease in entropy of the surroundings must be a value. No, that's not said well.
I like how you said that.
I don't like,
Somewhere else is getting.
yeah, this is horrible.
I know. I was very.
Who wrote that?
I'm broken down in different ways.
Yeah, no, that's, let me add that to my list of things to edit. That, what number is that? 27C. That, do you understand the principle? Okay, that, guys, I apologize. That's just poorly worded. That must have happened Friday afternoon at about 4 o'clock when I was ready to go home for the weekend. That's bad. You get the idea? Okay, so guys, let's get this in the books. Grab something to take notes with and on. And wait, don't close your books. Actually, open your textbooks to (809). All right, Sarah, are you good? Addie? Talmadge? Bailey, you good? 2 big thumbs up. Alice, you good? I'm glad. Jason? Emma, you good? Yeah? Grayson, how about you? Daniel, you good? Sage? Josh is not here yet. Jonah? Cody, you good? Robbie? Tucker? Ella? Leah, you good? Lise? And Riley? Caleb? All right. So, guys, again, the plan for the day goes like this. In the same way that, and we're going to pause and talk about that more. Guys, in the same way that we can quantify enthalpy, we can also quantify entropy changes. Things happening, disorder going up, disorder going down. We can put numbers to this. And guys, we can actually measure disorder in joules per mole. Typically not kilojoules per mole because it's not terribly energetic, but we're going to talk about that. Then, guys, as we do that, we're then going to talk about how this begins to also relate to spontaneity. Remember, we said that exothermic reactions tend to be spontaneous. Well, guys, it turns out that entropy also has a connection to spontaneity. Reactions that increase entropy also tend to be spontaneous. But, guys, that creates a tension, because sometimes one of those two factors, enthalpy and entropy, sometimes one of those factors works towards spontaneity and the other one works against it. And it's at that point that we're going to look at page, is it 809? It's at that point that we're going to look at the bottom of 809, and we are going to develop the ability to say emphatically this reaction is or is not spontaneous, as based upon the effects of entropy and enthalpy changes. So guys, that's going to be our day. So the first thing we're going to do is we are going to talk about quantifying entropy changes. Now guys, to do this, it's a little bit tricky. You may want to include this in your notes. So guys, unlike enthalpy changes, entropy changes. Did I say enthalpy the first time? Oh, good. Okay. I know, they really are. Why couldn't they have picked something different? At least the abbreviations are different, but neither of them make any sense. One is H and the other's S.
I don't like it.
I know. What if they were both just E or EN? Which reminds me, have you guys all seen the comedy sketch about the efforts to abbreviate all the names of the 50 states? Look it up on YouTube. The guy does drop the F-bomb, or not the F-bomb, the S-bomb. If you don't mind that, it's actually really clever. I can't because of that one word.
Just everyone yell at the same time.
Ah!
Just like mute it. Yeah, you could mute it.
Can we really?
Yeah.
All right.
The Greatest Showman today, and I swear it's so.
Really? In whose class?
Drama. He's on though. It was a sub.
Nice. All right.
This little old
That's
lady,
true.
It's just like, I'm the Greatest Showman, guys. I'm just like, oh.
That's awesome. All right, so guys, let's make sure we're clear on this. So what we're saying is that unlike enthalpy, it is hard to measure entropy changes. So maybe we should back out of this and talk about how do we observe enthalpy changes? What do we actually see when enthalpy changes? Temperature changes, right? So guys, our window into enthalpy changes are temperature changes. Starting to feel like the lab that you're about to do? Well, guys, it turns out that there is not an analog for entropy. When entropy changes, temperature doesn't have to change, which, Lee, is that whole idea with isothermal, right? You can have a huge entropy change with no temperature change. So what we do is this. Instead of working through it that way, what we do is we actually use experimental data for substances. So guys, I should have teed up this ball for you, but I neglected to, so let's do it now. Grab your AP equation sheets. And open up to page 4. The thermodynamics part, the thermochemistry part. All right, who needs one? Don't be shy, they're free. Come on. Who was it that used to hoard them last year? Jessica, that's right. Anybody? Oh yeah. Only if I can start calling you Jessica. Okay, so guys, do this with me. Looking at the thermochem part of this, third equation down. Delta H. How do you read the little circle? Not. It means standard conditions. Delta H naught for the reaction is equal to the sum of delta H naught sub F, which means what? The enthalpy of formation. And guys, that delta is important because what it's saying is this. Guys, don't miss this. That delta means the amount of enthalpy that changes when these substances are formed. Get it? Now go look at the entropy form of this, which is directly above it. What is missing? The deltas. Guys, these are not entropy changes of formation. Logically, this is completely different. When we think about enthalpy, when we think about enthalpy and quantifying it, we talk about how much heat is gained or lost when this was made. When we talk about entropy, we don't talk about how much entropy is gained or lost when this is made. We talk about how messed up is this thing regardless of how it got there. So these are not entropy changes of formation. These are entropies as that thing sits there on the table. If you've got a mole of an element, how messed up is it? If you've got a mole of a compound, how messed up is it? How disordered is it? What is its entropy? And guys, this is what this is all about. We don't talk in terms of entropy changes for substances. We talk about the entropies of them as they sit. Do you see the distinction? And we can then use those, as this equation allows, we can then use those to figure out the entropies of the overall process. So basically it goes like this. How messed up is the reactants? How messed up are the products? And the difference between them is how messed up the reaction changed messed up. Right? Okay. So guys, that's what that equation is saying. So along the way then, we need to talk about this idea of what are called standard molar entropies. They are abbreviated S naught, and they are measured in the units joules per mole Kelvin. Yep.
Why is it in Kelvin rather than Celsius?
That's a fascinating question. Let's talk about it. Let's let everybody write this down and then let's talk about it. The answer is pretty cool. Well, cold. Sorry, couldn't pass that up. So, guys, Talmage's question is actually interesting. Actually, it's his first interesting question. But let's talk about it. So, guys, first of all, this. We measure disorder in joules. There is an energy to disorder. Now, guys, what are the two factors that disorder is dependent upon? What's the denominator of the fraction? Amount and temperature. So, guys, fundamentally it means this. The more stuff you've got, the more screwed up it is. Right? If you've got a big ball of screwed up, that's more screwed up than a small ball of screwed up. But guys, it's also dependent upon temperature. But your question was, why Kelvin? And there's two answers. One, you'll notice that we're not talking about temperature change, right? When we think about enthalpy, we think about changes in temperature. But here we're not talking about changes in temperature. We're talking about empirical temperatures. The hotter something is, the more screwed up it is. Does that make sense? But what happens if temperature goes to 0 Kelvin? Well, that's absolute zero, right? And if that were to happen at absolute zero, what happens to entropy? It becomes zero. But doesn't that make sense? Because entropy is a measure of disorder. And if something is at absolute zero, it is completely still and it is completely organized, and entropy becomes zero.
But the Kelvin is in the denominator, right? So
Mhm.
if 0 is in the denominator,
Then it would make an asymptote. Well, no. So you're not dividing by zero. The idea is that as these things, I mean, we'd have to set up the math, and we're not looking at the equations that we actually use to calculate entropy, but the thought is that they are related to these two things. Not that you're dividing by zero, kind of, but the idea is it is related to Kelvin temperature and not Celsius because they share a common 0 point. Because when the temperature becomes 0 Kelvin, the disorder also becomes zero. So, which kind of gets us back to this idea of experimental data being used to we're never going to look at the equations that are required to calculate entropies, but they are actually equations that take into account mass and temperature, or moles and temperature. So, you guys good? All right. So, guys, these then become the guidelines when you're thinking about entropy. And guys, I would circle, highlight, star, asterisk, whatever you need to do, because if you don't get this, you are going to get beat up by the AP graders. Guys, they love to niggle these points. So guys, these are the fundamentals that you need to understand about quantifying entropy. Guys, number one, this. The entropies of the elements are not zero. Remember we said the heats of formation of the elements are zero? But guys, the entropies of the elements are not zero. And elements are messed up just like any other form of matter. So while the heats of formation of the elements are zero, the entropies are not. Then guys, number two, and we've alluded to this, but now we're saying it outright. Entropy is phase dependent. Gases are more screwed up than liquids. Liquids are more screwed up than solids. So guys, what else does entropy depend on? Next thing, molar mass. The fatter something is, the wigglier it is. You're going to find out in a couple of units, we call that polarizability, but we'll get there later. So guys, the bigger, the more massive something is, the more stuff it has to wiggle, and therefore the higher its entropy. Yeah.
Says 10 that way. Are there exceptions?
Oh, sure. Yeah. I mean, there's exceptions to all of these, but we can, just be vague. You'll be fine. Guys, next one. The entropy of a substance tends to increase with the number of atoms that make up the thing. Understand that is not just restating the previous one, because atoms have different masses. So you could have more atoms in a lighter molecule depending upon the mass of those molecules. They would never ask you to split those hairs, but understand if you've got two molecules that are made of the same number of atoms, if one's more massive, it'll be greater. But if one's got more atoms and their masses are similar, then the one with more atoms will be greater. And then, guys, finally, this one. This is a little thing I like to call question number 6, right? Remember how we talked about N-pentane and neopentane? That was a precursor to this, that entropy tends to increase with elongation. So guys, let me just sort of lay this out for you. These you'll see in multiple choice. These are not big ideas, these are little ideas. Hey, this molecule's longer. They might give you neo and N-pentane and which one is a greater entropy, things like that. Guys, this one is huge. They will throw questions at you that say, this reaction goes from liquids to a gas. What is the change in entropy? You've got to understand that gases have higher entropies than liquids or solids. And then liquids more than solids. And guys, by the way, we should mention this. If you see questions like that, you have to establish the fact that it goes gases, then liquids, then solids. So if you had a reaction that goes from the gas phase to the liquid phase, what's happening to entropy, up or down? Entropy is going down. But here's the way that you have to talk about that. You need to say gases have more entropy than liquids. So when this reaction goes from the gas to the liquid phase, that indicates a decrease in entropy. You see what I'm saying? You have to establish the principle before you apply it in any particular circumstance. And guys, don't shoot the messenger. When I first learned about this, it drove me nuts too. I thought it would just be enough to say a gas is becoming a liquid, so the entropy is going down. But the AP authors will not give you credit for that. You actually have to first establish that gases have more entropy than liquids, then apply the principle in this particular example. You see what I'm saying? So, yeah.
Just on that, so eventually we'll go down, eventually like somewhere else in the universe will go up.
Correct, but we're always talking system. So the question would actually say, what is the value for delta S for this process? But what you're saying is true. There's got to be somewhere where entropy is going up. And they ask very, very few questions about that. But this question would be stated, what is delta S for this process? Yeah. You guys good? Are we settled? Yeah. Oh, Leah, was that, or just... Okay, sounds good. All right, so guys, with that said, and then given this equation, right, you don't need to write it down, it's in your thing. But guys, remember what's missing from this equation? No. N's, right? Numbers of moles matter. And guys, I didn't put it in this one because remember the equation sheet doesn't put it for any of them. But guys, there need to be N's in all of these because all of these are molar relationships. I don't know why it's not there, but remember to keep track of the coefficients from the balanced equations. Sorry, I'm hiccuping. Is that okay? Okay. All right. So guys, with that then, Just like when we did enthalpy calculations, we just go products minus reactants, plug in the values, off you go. You're also going to be doing a few of those with entropy calculations. And it would read something like this: calculate the delta S for the synthesis of ammonia from N2 and H2. Guys, please don't write this down, but you might go N2 plus H2 yields NH3, and this balances with a 2 and a 3, and then it would be change in entropy is equal to the sum, and you just go from there, right? Products minus reactants, multiply by the coefficients, look up the numbers, do the math. Yeah? Okay, then let's not do it. All right, so guys, this is about to get conceptual, and this is it. What's it say? The big idea for the whole unit. Guys, this is the stuff that the AP authors are going to hold your hand to. That didn't come out well. Let me say it differently. This is where they're going to kick your butt. Is that better?
Yeah.
All right. So guys, remember, spontaneity is the big idea, right? So can I get an amen for these next two thoughts? All spontaneous reactions are exothermic, tend to be exothermic. So, hallelujah. So all spontaneous reactions, they tend to be exothermic, right? They release energy. The quick cold pack was an example of an exception. But guys, exothermic reactions tend to be heat losers and not heat gainers. Are we in agreement on that? Now guys, we have another related idea relative to entropy. Spontaneous processes tend to increase the entropy of the universe. Now we understand the second law of thermo. We know that if a process is decreasing entropy, there's an offsetting increase somewhere in the universe, and on and on and on. But guys, when we're talking about spontaneous reactions, they themselves tend to create increases in disorder. Are we all in agreement on that? If we're not, you need to change your thinking. You okay? All right. So guys, this then leads us into the last thing we're going to talk about today. This unit. And guys, it's all about spontaneity. So, guys, what we need a way to predict spontaneity. Because we've got two factors. We've got heat exchange and we've got disorder changes. And both of these play a role in whether a reaction is spontaneous. But how do they come together to finally predict spontaneity? And Jason, you're going to be glad to know this is not a tends to, this is an always. This will always predict spontaneity. And guys, the way these come together is in a form that we call Gibbs free energy. You will also hear this termed free energy. Either is fine. If you're interested, guys, this is actually a thermodynamic thing that this guy named Gibbs came up with when he was actually working on inventing more efficient steam engines. Because what he found is a lot of times steam engines burn a lot of coal, but you don't get a lot of energy out. So he was trying to figure out where the energy went, and guess what he figured out? It was going into disorder. That the energy that was not making steam to drive the train was leaking somewhere, and it was leaking into disorder, and he's the one that actually proposed this idea of entropy. Anyway, all of that to say, what is Gibbs free energy? And guys, it is simply a thermodynamic function that brings together enthalpy and entropy. It just brings them together. Now, you ready for this? What could its abbreviation possibly be? It's G. Hey! All of a sudden, the universe is right again. I know. Two wrongs makes a right. So how does it come together? Guys, this is beautifully simple. G is equal to H minus TS. That's it, guys. Gibbs free energy is simply the enthalpy minus the temperature times the entropy. But we need this in a different form, because when we are doing thermochemistry, these things are changing. So we just huck a delta in front of all of them. Technically, probably. What does it give you on the AP sheet? Because this is on there. Oh, it does. So guys, this is on the AP equation sheet. And it should have the knots, the standard conditions parts. Mine just doesn't.
What is temperature measured?
Kelvin. Has to be in Kelvin.
Why is it not changing?
Because the temperature does, guys, Addie under her voice says, why is it not changing temperature? And while the temperature could be changing as a result of enthalpy, this is a deep thought. I'm going to lay it out there for you. While the temperature could be changing because of enthalpy, this is weird, the amount of energy that's being exchanged does not depend on temperature. So you could have a reaction at 50 Kelvin and it could lose 100 joules of energy. But that same reaction at 100 Kelvin would also lose 50 joules of energy. So the amount of energy gained or lost is not dependent on the temperature the system is at. It causes a temperature change, but it's not dependent on the temperature. Do you see what I'm saying? That is not true of entropy. Entropy is temperature dependent. A reaction actually has different entropies at different temperatures, and so it belongs in this part of the function.
So is that like temperature initial?
It is the temperature at which the reaction is happening. With the, in your thinking, ouch, in your thinking it's initial, because it's the temperature that the reaction started at, with the understanding that as it gains and loses heat, its temperature will change.
Okay.
Is that okay? Go ahead, Caleb.
So will absolute temperature kill all of the
I don't know. Yeah, so in the first one, the Q is equal to MCAT. It doesn't matter because Kelvin and Celsius temperature changes are equal, right? And then the only other place that temperature shows up, and we're going to talk about these other forms later, they have to be in Kelvin. Yeah, okay. All right, so guys, this is then the bottom line, end of story, answer to the question, is a reaction spontaneous? Does it depend on enthalpy? Yes. Does it depend on entropy? Yes. But, guys, the overall answer is this. The sign of delta G tells us, without exception or question, the spontaneity of a reaction. So guys, if delta G is negative, that bugger's spontaneous. Bugger is spelled with 2 G's. If delta G is negative, that reaction is spontaneous. But guys, notice the way we say this. The reaction is spontaneous in the forward direction. You can also hear some people will say it is spontaneous in the direction written. So guys, fundamentally what that means is this. A is turning into B, and if delta G is negative, A turns into B all on its own. You understand that? Okay. Now guys, what about this? What if delta G is 0? What's it doing? Both of them. It's at equilibrium. So guys, if delta G is 0, the reaction is going both directions simultaneously. That's equilibrium.
How does isochemical work?
We would have to talk about specific examples. Can we just let that be okay? Okay. So, guys, what is it, and you see where this is going. What if delta G is positive? So the reaction is non-spontaneous as written, but guys, think through this with me. If delta G is positive, the reaction is non-spontaneous this way. But does that mean nothing is happening? No. What it means is it's going this way. What it means is it's going this way. So if delta G is positive, the reaction is not spontaneous in the forward direction, but it is spontaneous in the other direction.
Wait, so it will be instantaneous in the reverse
Mhm.
direction?
Yep.
So all spontaneous reactions have
So all reactions have without outside intervention, all processes have a direction that they always go, and they have a direction that they never go, without outside intervention. We call it the spontaneous direction and the non-spontaneous direction. And so when we write these things out, if we get a delta G that's positive, it just means that it's spontaneous the other way. This is going to become really important in chapter 20 when we start building batteries. Because if you build a battery and that battery has a positive delta G, it simply means the current's flowing the other way and you just picked the wrong poles to build your battery. We'll talk more. So, you guys good here? Good? All right. So guys, one more thing to talk about then, and we're ready to get into the final stuff for the unit. So guys, it goes like this. I wouldn't even write this down because it's really just a retelling of what we've said before. Really, only write down the things that you go, really? But you shouldn't say really. So guys, when I think about free energy, I think about a ball rolling downhill. And we've been talking about this all along, which sort of brings this together. Guys, why do balls roll downhill? They lose energy. And did you notice I was fudging it a little bit? Because we said when the ball loses energy, it loses energy in the form of heat. And it kind of does. But guys, now we can finally say it. When balls roll downhill, they lose energy. What kind of energy? Gibbs free energy. If we could study the heat and entropy changes in this process, we know that balls roll downhill, and the reason is because this thing is losing energy. But the energy that we need to finally be talking about is Gibbs free energy. And we don't need to dig any deeper into that. What we do need to understand is that anything that is spontaneous is losing energy, Gibbs free energy. So what that tells us then is this, that any spontaneous process, the free energy will always decrease. It'll be negative. Is that okay? So guys, what that then tells us is this, that if we do similar calculations with Gibbs free energy, if we end up with the Gibbs free energy less than 0, that means that that thing is going to products, right? Think about this. If we have reactants and if we have products, and if delta G is negative, this thing's making products. Guys, what if delta G is positive? What's this thing doing? Going the other way, and it's making reactants. And what if delta G is equal to 0? It's doing both. So that's the bottom line. If delta G is negative, this thing's going to products. If delta G is positive, it's going to reactants. And if it's 0, it's at equilibrium. Is that okay? Go ahead.
So in this table, the bottom of this page.
We're not there yet. Yep. That's next. Go ahead, Robbie. Let's not go too deep. So can we say this? That balls roll downhill because they lose energy. Are we in agreement? Then we'll try it. Go ahead.
I was noticing that if you take delta G and it's like the slope,
Yeah.
that if the slope's negative, then the ball will, it's spontaneous. If the forward direction, it will roll down.
Which actually is not bad if we can say that this is energy. That should be E for energy. If this is energy, what would this be? It's not always time.
Yeah, that's the weird. I would just
Yeah, I like it. There, yeah, so if it's 0, I just need some X units. Then we got slope. I like it. All right. All right, Leah, you ready? Here we go, guys. This is then what you're going to see in free response on the test. Do not write any of this down. Think and learn rather than write. You ready? Here's what we got. So guys, we have this equation. Gibbs free energy, change in Gibbs free energy is delta H minus T delta S. Now, guys, here's what we've said. Delta G is free energy. Delta H is enthalpy. Delta S is entropy. So guys, we have an entropy term and we have an enthalpy term, and this leads to our Gibbs free energy term. Now, these are the things that we've agreed upon. That free energy is the bringing together of enthalpy and entropy. And here's what we've said. Delta H, if it's positive, it's endothermic. If it's negative, it's exothermic, right? Does that sit okay? Okay. So, which one of those two tends to be spontaneous, top or bottom? Which one of those two tends to be spontaneous, top or bottom? Bottom. Things that are exothermic tend to be spontaneous. I made way too big a mess. Let me just underline it. So guys, things that are exothermic tend to be spontaneous. Now here's the other thing that we've said. When we talk about entropy, guys, we've got a little bit of confusion going on. So the idea is this. Entropy is actually this entire statement. But now we have an interesting changing of signs. So I know you're trying, just think through this with me quickly. So guys, increase or decrease in entropy, which tends to be spontaneous? Increase, right? But here's the thing. We actually consider this entire term to be our entropy term. But now let's have a deeper conversation. So guys, when we look at this entropy term, first of all, the temperature is dependent upon absolute temperature, which is Kelvin temperature. And guys, what can Kelvin temperature never be? Negative. So guys, temperature is always positive. So here's the idea. Guys, temperature is always positive. Now, what if delta S is positive? Does that lead towards spontaneity? Does positive delta S, will that be spontaneous? Probably. But guys, look at how this all comes together. So the idea, temperature is always positive. It's Kelvin. If delta S is positive, when you multiply these together, what will you always get? Positive number. But then you're going to subtract it. You're subtracting a positive number. And if you're subtracting a positive number, what will that tend to make delta G? Negative, and that indicates spontaneity. Good? Now let's try this. Guys, what if the opposite is true? What if delta S is negative? Well, guys, if delta S is negative, temperature is always positive. So what kind of number will this product be? Negative, but then you're going to subtract it, which is functionally the same as adding, and that tends to push delta G towards the positive, indicating non-spontaneous. So guys, now we've got battles going on. Ready? So what if delta H is negative? Spontaneous or not? Probably. Let's do this. Spontaneous is too big a word, right? Because let's do this. Spontaneous is going to be good, and non-spontaneous is going to be evil. Okay? The battle between good and evil. So here we go. Negative delta H, good or evil? Good, right? Are you catching the good and negative? Okay, spontaneous. Now, let's do this. Positive delta S, good or evil? Good. So guys, we've got good and we've got good, but let's go through the math. This is always positive, right? So if that's always positive, what is the value of this going to be? Negative. So this is negative. The value of all of that is negative. So what will that always make delta G? Good. It's negative. Spontaneous, right? Now guys, look at this. What if delta H is positive? Good or evil? Evil. That's not spontaneous, usually. Now guys, what if delta S, what if the change of entropy, what if disorder is going down, good or evil? Evil, oh, that's bad. That doesn't lead to spontaneity. But now let's look at Y. What is a negative times a positive times a negative? Positive. So that's bad. That doesn't lead to spontaneity. So guys, this reaction will never be spontaneous. This doesn't lead to spontaneity. That doesn't lead to spontaneity. That thing will never be spontaneous. Now, does that mean nothing's happening? No, what's it doing? Going the other direction, right? It's going the other way. But now, guys, what if one of the terms is good and one of the terms is evil? Who's the tiebreaker? Temperature. And guys, that leads us to this table. So guys, if you want to look at my version, that would be fine, but you also have it at the bottom of your book. 80 what? 9? Okay. So guys, check this out. Do this with me. Let's pick the easy fruit first. Delta H is negative. I am not right-handed. Delta H is negative, good or bad? Good. Delta S is positive, good or bad? Good. This thing is always spontaneous. Now, delta H positive, good or bad? Bad. Delta S negative, good or bad? Bad. This is non-spontaneous at all temperatures. But that doesn't mean nothing's happening. It just means it's going in the other direction. But now, guys, watch this. This is where this gets interesting. I want to zoom in so you can see this a little better. Now let's talk about, Now let's talk about the tiebreakers. Delta H is negative, good or bad? Good, right? Yeah, exothermic, spontaneous. Delta S is negative, good or bad? Bad. So here's the idea, guys. If we want this to be good, spontaneous, if we want this to be good, we have to decrease the influence of evil. So how do we do that? Well, we make this thing cold. Because if we can drop the temperature, then the impact of the entropy change, evil, which is working against spontaneity, we can decrease. And so if we drop the temperature, then the value, the entropy change, which is working against spontaneity, that is minimized, and as a result, the reaction can be spontaneous. So this is spontaneous at low temperature and becomes non-spontaneous as the temperature goes up. Don't ever say good and evil on the test. Okay? You've got to understand it through the terms, but that's the logic. So guys, what about this? Positive delta H, good or bad? Positive delta H is bad. That's endothermic. Evil. Positive delta H is evil. Positive delta S, good or bad? Good. So now I want good. Now we want good to overcome evil. But now the good is the entropy thing. So if the entropy thing is good, we gotta heat this thing up to get more good to overcome bad thermic. So this spot is I don't like the way this becomes spontaneous at high temperatures, and at low temperatures it's non-spontaneous. So this thing we've got to heat up to make spontaneous. Do you understand the logic? So guys, if you understand the logic, there is one important question that we've got. Lies this whole conversation. What does hot and cold mean? Right? If this is the case, it always goes. If this is the case, it never goes. But guys, down here where we have competing factors, the question that we need to talk about is what temperature, how hot or how cold do these have to become? So guys, I turn that question to you. How could you calculate the temperature at which these things become spontaneous. Let me do this. Do this with me. So let's take a fictitious process where simply reactants become products. And the delta H for this process is, I'm just going to use simple numbers, 10 kilojoules per mole. And the delta S for this process is positive 275 joules per mole Kelvin. So guys, given this data, how could you figure out the temperature at which this thing will become spontaneous? Go ahead, Bailey. Okay, so let's get the equation. Delta G is equal to delta H minus T delta S. So I like what you're saying. Plug in the values, right? But what are we solving for? T. So we got a problem. We're given delta H, we're given delta S, we're solving for T. But we have two variables in one equation. Not make up a value. There's a value that will allow us to nail this tight. Go ahead, Alice. Set it equal to 0. Because, guys, which one is it? At 0, is a reaction spontaneous or not? It's neither and both. It's at equilibrium. Do you see it? So what we're going to do is we're going to set this equal to 0, and then delta H is plus 10 kilojoules per mole minus, I'll leave it T, times 275 joules per mole. Guys, write that down and then stop. Don't solve it. Yeah, thank you. So guys, let's have a couple conversations. Well, no, let's save that for later. Let's have this conversation. Why can't you solve this as written? Your units are different. You can't bring together joules and kilojoules. Let me make a suggestion. Guys, don't convert kilojoules to joules, because when you do, you end up having to multiply by 1,000, and it's a place to make mistakes. Guys, I would strongly encourage you to convert joules to kilojoules, because all you got to do is drop a decimal place in this thing 3 places over. You've got to bring your units together, though. So now we end up with this. Negative 10 is equal to negative 0.275. I hate T. I want to make it X, but I won't. Right? Then dividing 10 divided by 0.275. T is equal to 36 Kelvin. Yeah, understand I made up these numbers. That's cold. You okay on the math?
No, how'd you get 36?
10 divided by 0.275. Is that okay? Okay. But guys, understand, this work on the AP test is worth 0 points, because this is not the answer. Remember, the question that we asked was, at what temperatures is this reaction spontaneous? This is not the temperature at which this is spontaneous. This is the temperature at which it's at Equilibrium. So now you got to use your brain a little bit. Because, guys, 36 Kelvin is the tripping point. But here's the important other half of the question. On which side of 36 is this thing spontaneous? Above or below? And this is where we talk about good and evil. Ready? Plus 10 kilojoules. Let me say it differently. Delta, let's go up here. Delta H is positive, good or bad? Bad. Delta S is positive, good or bad? Good. Which means in order for this thing to be spontaneous, we want the impact of delta S to be greater. Remember that logic? So will this be spontaneous above or below 36? Above. So the answer to this, which I would encourage you to write out as a brief sentence, is this reaction will be spontaneous at any temperature above 36 Kelvin. Not inclusive, because at 36 it is not spontaneous. Just a second, Alice. At 36 it is not spontaneous, it's at equilibrium. So the answer would be this reaction is spontaneous at any temperature above 36 Kelvin. Go ahead.
Sorry, I was just yawning as well. But I have a question. So can I just write like spontaneous and then use the little Pac-Man symbol and then write
You could,
36?
yeah, so
Holding it like,
no, you can do that, but the alligators always scare me. So you could go temperature spontaneous greater than, yeah. I guess the only way you could screw that up is if you did that,
Yeah.
or if you did the alligator the other way. Do you guys think of alligators too? The alligator eats the big number?
That's how I always.
Oh yeah. All right, guys, here you go.
Alice is for it. Nice.